Hello, everyone. Welcome back to our Finite Element Method lecture series. In the previous chapter, we learned what the finite element method is and why it has become one of the most powerful numerical techniques in engineering. Now, in Chapter 2, we begin with the first and most important step of FEM, discretization. Before solving any engineering problem, we first need to convert a real structure into a mathematical model. This is exactly what discretization helps us do. Let's first look at the chapter contents. In this chapter, we will study discretization, finite element types, degrees of freedom, mesh generation, element connectivity, local and global coordinate systems, shape functions, and the convergence concept. These topics form the foundation of every finite element analysis. Now consider the flowchart shown in the center. Suppose we have a complex engineering structure, such as a bridge, a dam, a building, an aircraft wing, or an automobile body. These are called continua because they behave as continuous bodies. Such structures are too complicated to solve directly. Therefore, instead of solving the entire structure at once, we divide it into many small and simple pieces. This process is called discretization, and each small piece is called a finite element. Once the structure is divided, we apply mathematical equations to every individual element. Then, all the element equations are assembled together to represent the complete structure. Finally, by solving these equations, we obtain approximate values of displacement, stress, strain, temperature, or any other required response. So remember the basic idea of FEM. A large engineering problem is converted into many small problems, and these small problems together provide an approximate solution. This is why the finite element method is both practical and efficient for solving real engineering problems. Now that we understand the overall idea, let us study the first step in detail.
What is discretization? Discretization is the process of dividing a continuum into a finite number of small parts, called finite elements. But what exactly is a continuum? A continuum is a real engineering body that behaves as one continuous object. Since every point inside the body can deform, it theoretically has infinitely many unknown values. Solving an infinite number of unknowns is impossible, so we divide the body into a manageable number of elements. Let's understand this with the plate shown in the figure. Initially, we have a continuous plate with a circular hole. One side is fixed, and external forces are applied from the other side. In the second step, the plate is divided into many small regions. This is the discretization process. In the final step, nodes are placed at the corners, and these nodes are connected to form finite elements. The complete network of elements and nodes is called the mesh. A mesh is simply a mathematical representation of the real structure. Now, notice the different mesh types shown below. A regular or structured mesh has elements arranged in a uniform pattern and is suitable for simple geometries. An irregular or unstructured mesh contains elements of different shapes and sizes and is useful for complicated structures. A mixed mesh combines both regular and irregular regions to achieve a balance between accuracy and computational efficiency. Now, remember these three important definitions. Every small part is called a finite element. The points where elements meet are called nodes. And the collection of all elements and nodes is called the mesh. So the complete FEM process starts with a continuum, converts it into elements and nodes, creates a mesh, and finally builds the finite element model. But this raises another important question. What exactly are elements and nodes?
A finite element model is made up of elements connected together at nodes. Let's first understand what a node is. A node is simply a point where two or more elements meet. Although a node has no physical size, it is one of the most important parts of the model because all unknown quantities are calculated at the nodes. For example, displacement, temperature, pressure, and rotation are all evaluated at the nodes. Now let's understand an element. An element is a small portion of the original structure that connects two or more nodes. Each element represents the physical behavior of that small region. Depending on the problem, elements may be one-dimensional, 2-dimensional or 3-dimensional. A 1D element represents members like bars, rods, springs, and trusses. A 2D element is used for plates, slabs, walls, and shells. A 3D element represents solid bodies, such as concrete blocks, foundations, and machine components. The poster also shows some common element shapes, including bar elements, spring elements, triangular elements, quadrilateral elements, tetrahedral elements, and hexahedral elements. The choice of element depends on the geometry of the structure and the type of engineering problem being solved. Finally, notice the colored mesh shown at the bottom. Although the elements are separate, they are connected through common nodes. This connection is called element connectivity. Connectivity allows all individual element equations to be assembled into one global system of equations, representing the entire structure. So always remember these 3 key concepts. Nodes store the unknown values. Elements represent the physical behavior of the structure. Connectivity links all the elements together to create one complete finite element model. These are the fundamental building blocks of the finite element method. In this lecture, we learned how a real engineering structure is converted into a finite element model through discretization. We also understood the meaning of nodes, elements, and mesh, which are the basic components of every FEM analysis. In the next lecture, we will explore the different types of finite elements, understand degrees of freedom, and learn how engineers generate an efficient mesh for accurate analysis. Thank you for watching. If you found this lecture helpful, please like, share, and subscribe to support the channel. Don't forget to press the bell icon so you never miss the upcoming lectures in this finite element method series.